So, stability from the transfer function. So we've defined it. Notice that our definitions of stability, and specifically the one we're going to use, the free response definition of stability. It's a stability that's broad enough to encompass different ways of finding that stability, right? Or showing that a system is stable or unstable. So we're going to specifically look at stability from the transfer function. That's how we're going to determine if a system is stable. So from our definitions in terms of the free response, we see that a closed loop LTI system is asymptotically stable if all its poles have negative real parts. In other words, they're in the left half plane. So remember, we talked about poles being what governs stability before, right? And remember that poles are also equal to what? Eigenvalues of the A matrix, if you have it in terms of a state space model. And they're also equal to one other thing. Roots of the characteristic equation. I know you couldn't even see who said that, but yes, roots of the characteristic equation. Good job, somebody. So although we're going to talk about poles right now, it's the same as if we talked about eigenvalues, and it's the same as if we talked about roots of the characteristic equation. So, stable if all of its poles are in the left half plane. Conversely, and what's the left half plane? That's the complex plane, right? So the negative real part is in the left half plane because real is the x-axis, right? So conversely, a closed loop LTI system is unstable if it has at least one pole with a negative or with a positive real part. So at least one with a positive real part. In other words, one in the right half plane, and or has poles of multiplicity greater than one on the imaginary axis. This one's a little bit more subtle, but it's also true. We didn't talk about that one before, or maybe we did. It's a subtle point, and it arises from the fact that if you have a pole of multiplicity greater than one, so there's like two on top of each other, a double pole we call it, or a triple pole or whatever, you're going to end up with, remember in your solution to the differential equation, that's not going to contribute just an e to the minus lambda t. It's going to contribute a t. Well, one of them will be e to the lambda t. The other one's going to be a t e to the lambda t, remember? And then if it's multiplicity 2 or 3, then you have t squared e to the lambda t. So if that lambda has a negative real part, then the exponential dominates the polynomial, okay? And you still get a decay to 0. But if that exponential is purely imaginary and doesn't decay to 0, then you're going to have the linear growth of a sinusoid, which is bad news. Or of any system. So the multiplicity thing comes from the solution, including a factor of t or more for multiplicity. So finally, a closed loop LTI system is marginally stable if it is not unstable but has at least one pole with 0 real part, in other words, on the imaginary axis, and if none of these has multiplicity greater than 1. So that would be marginally stable. So let's look at an example. So we've been talking about, because we care about closed loop stability, right? We care about the closed loop stability, so we're always talking about closed loop here. Open loop can be stable or not stable, but closed loop can still be stable or not stable as well. So you can either make a stable system go unstable by closing the loop, or you can make an unstable system go stable. Typically, we want the closed loop to be stable. That's our number one goal, right? Stable closed loop system. So, stability of a closed loop transfer function from its poles. So given the plant transfer function, so this is not the closed loop transfer function, we have to find that. Find the unity negative feedback closed loop transfer function and comment on its stability. Let the command be R and the output Y. So this is our G. So remember that the plant shows up in the feedback loop. So let's draw this little feedback loop over here again. Plus negative feedback, I said, so minus. There's a controller, C, which it didn't say here, but we're gonna set this to unity. It wasn't given in the problem, so we're gonna say just 1 in this case. And our plant, G, and then that's our output, and we have our unity feedback. So that is our closed loop transfer function, or that's our closed loop block diagram. We want to have a command R giving us an output Y. We want that transfer function. So remember, we did this closed loop transfer function derivation. It's not too bad. We did that in chapter 1. We said that the output Y of S over the input R of S is equal to, do you guys remember? It's good to kind of commit this one to memory. So it's the forward loop stuff, so it would be GC, but in this case, C is 1. So we have G over 1 plus CG. So 1 plus G. So let's go ahead and just plug that in. Plug in our G. So we have 1 over S squared plus 3 divided by 1 plus S squared plus 1 over 1 plus S squared plus 3. And let's go ahead and simplify that. We can drop this this denominator down here, cancel with that one. So we end up with 1 over S squared plus 3 plus 1, right? Which is just equal to 1 over S squared plus 4, which, well, I'll just leave it like that. So the poles, so it's poles, PI, how many of them are there? 2 poles, right? Second order. So it's poles, PI, can be found by solving for the values of S for which the denominator is equal to 0, right? And so what values are those? So it's so negative 4 over here, so you're going to have plus or minus J2, right? Because square root of minus 1 sneaks in there. So both poles are on the imaginary axis. So I'll just do a little pole plot here, pole 0 plot. So plus 2 and at minus 2, J2. And so they're on the imaginary axis, and therefore, what is the system? What's the stability status of the system? Sorry? So there's 2 poles on the axis. Are any of them double poles? Is there any multiplicity on the axis? No, there's not. because they're not on top of each other, they're distinct even though they're plus or minus. So they're not on top of each other, therefore there's only multiplicity 1 of each of them. And there are no poles in the right half plane, so therefore the system is, it's marginally stable, right? So we have an oscillation that occurs. If you have an initial condition, remember we're using the free response definition. If you have an initial condition, you let it go, it's going to oscillate. There could be poles over here, it'd still be marginally stable if we still have these poles on the axis. But if one was over here, if any pair was over there, or if one was over here, it would be unstable, right? If we moved these poles over to the left, it would become stable. But they're on the axis, therefore it's marginally stable. Okay, now comes a really fun section. Stability from the form of a closed loop transfer function. So let A, B, and C be constant coefficients, and the denominator of a closed loop transfer function be this polynomial, with the bn's being the coefficients written out as a nice big polynomial in descending order. And on the other side, we say, okay, we could factor this, right? We could factor this out. We would get all of these other coefficients, A1, A2, and then there might be some overall factor C that's out front. So this is, these are two different ways you could write the denominator of a closed loop transfer function. If a system is stable, it must have all left half-plane poles. So all of the AI must have negative real parts. Notice that this is written such that the AIs are poles. If S is equal to A1, this all goes to 0, right? So that means that all the AI, all the poles must have negative real parts, which is not obvious, and I'm not going to prove it, but I will just state this. It implies that all of the BI must be positive, and additionally, all of BI must be non-zero for I between 0 and n. In other words, there are no missing powers of S. So there's none of these. So if you're going to have, so you have to be very careful about this. So if the system is stable, all the BNs are non-zero and positive. Okay? It's very specifically in that way. So it doesn't go the other way. So the system can still be unstable if you have all positive Bs. But if it's stable, it must have all positive Bs. Okay, so that subtlety with logic, we're going to go through that. It's going to be really fun. I know that you guys love you some logic, so we're going to go through it. So however, these BI conditions are merely necessary conditions for stability, meaning that they are necessary for stability but not sufficient, meaning something more is needed to ensure stability. So let's look at this little footnote here. This term necessary and sufficient always is confusing to people. The first time that I saw it, and actually for several times I saw it, it was really confusing to me. Threw me off. But this should explain it in a little footnote, no problem. Okay, so here we go. A logical statement, P implies Q. You can also read that, if P then Q, right? Means P is sufficient for Q, and Q is necessary for P. Okay, so this is the necessary and sufficient. These two terms, you can always go back to this simple statement if you want. Write this logical P implies Q, then P is sufficient for Q, Q is necessary for P. That is, if P, then Q is sufficiency, and if not Q, then not P, which is necessity. Necessity and sufficiency are duals. So now we're going to talk about our specific system. Let P be the system is stable, okay? And Q be all BI are positive. Then if any BI is negative, which is to say not Q, then the system is unstable, which is to say not P. If Q, so another case, but if Q, it does not necessarily follow that P. In other words, more information is required. So, if you look at your denominator of your transfer function, and you say, all of these b's are positive. All the coefficients are positive. One's 4, one's 7, one's 3.2. You say, the system might be stable. But if there's a missing factor, so say one of these is 0, or one of them or more of them are negative, okay? Then you can say, totally, you're sure, so you know in that case, not Q, you know that the system is unstable. So you can test to see if the system is unstable by looking at the signs of these coefficients, but you can't test if it's stable. All right. So I know that's a little bit abstract, but let's do an example. So let's talk about stability of each of these 4. So G1. The poles are obvious from this one. It's already factored, right? The poles are -3, -10, and -22. So is this system stable, unstable? What can we say?
It might be stable.
Well, we say that it is stable because we know those poles. If we know the poles, we're good, right? If the poles are all negative real part, we know it's stable. So we can just say, just by inspection, G1 stable. G2, what can we say about G2 just by inspection? I'm seeing this guy right here. There's a negative, which means that not Q, right? So we mean not, so that means not P, which is it's unstable, right? We can test for instability, which is this way, as we know just by inspection, unstable. We didn't even have to find the poles. G3, we look at that. What can we say about it? Yeah, the s squared term is 0, coefficient 0, therefore unstable. We can test for instability without even having to solve for those poles. What about G4? There's nothing missing, they're all positive, so maybe stable. We have to solve for poles. Or we'll use this trick that is what the next lecture is all about, the Routh-Hurwitz criterion. So this is the way to look at a transfer function and say, stable, unstable, maybe stable, etc. Okay?